So if we combine our three processes into one equation, if we want to see how does dN2 change with respect to time if we have all three processes happening simultaneously, which is what's going to happen in any real system, we're going to have an equation that looks like this. We'll have the difference between N1 and N2 times our Einstein B coefficient. We can pick B21 or B12, they're just equal to each other, times the spectral radiation density at the frequency we need for the spontaneous emission or absorption, sorry, not spontaneous, but stimulated emission or absorption to happen. And then we'll also have our spontaneous emission that's happening minus N2 times the Einstein A coefficient. All right, you can barely see that. All right, so I didn't block it with my face. So at equilibrium, so once we shine light on, eventually reach an equilibrium, and we'll get no net change of the number of molecules in state 2. So at equilibrium, this rate of change will go to 0. And one thing that's interesting about that is it lets us solve for the relationship between B21 and A21. So that's not particularly relevant for us right now. The equation is in my notes that are posted. But the key part for us is thinking about what's happening at equilibrium in terms of the relative populations, right? So in terms of N2 versus N1. Well, one thing we know is that we can describe the number of molecules in different states by the Boltzmann distribution. And so according to that distribution, if we have N2 over N1 is going to be equal to an exponential that's based on the difference in energy between the two states divided by the Boltzmann constant times temperature. And temperature here has to be in Kelvin. Or we can rewrite this, that we know that this difference in energy is the same as the frequency of light times Planck's constant over kBt. Okay, so the question is in a laser, what we're looking for is we want stimulated emission. All right. And in general, when we're talking about the Boltzmann distribution, what this tells us is that the population of N2 will always be less than N1. That's what the Boltzmann distribution tells us. Whatever's higher energy, provided the degeneracies are the same, which we're assuming they are in this case, that they're singly degenerate, whatever's higher energy will have less molecules in it than whatever's lower energy. And that's regardless of temperature. As the temperature increases, they get closer to even, but even at infinitely high temperature, the distribution will only ever become 50-50. And for stimulated emission to dominate, we need the opposite. We need N2 to be greater than N1 for stimulated emission to dominate our process. Otherwise, we'll mostly get absorption of light, and instead of getting extra photons, our photons will disappear as they get absorbed by this molecule. And so this requirement for a laser, the fact that we need N2 greater than N1, this is what's known as a population inversion, because this is not what molecules will do on their own, right? If we just have a system without any external factors on it, population inversions don't happen naturally. You need some way to drive them in a system. And this is at the heart of creating a laser, is we need this population inversion so we can actually get the stimulated emission and get the amplification of light, get more light out than we put in, right? If we don't have that case, when we put light in, it'll get absorbed and we won't be able to make a laser.